Right, so I need to just.
Yeah, use a mouse.
Okay, so our second speaker is Kamilla Rekvényi from University of Manchester. Will be telling us about symmetry from graphs to groups and back.
Thank you for having me. And just because Piotr said that defining graphs would insult some people's intelligence, I will define graphs and I will define groups because I was under the impression that some people might not know these things. But please don't feel insulted. Okay, so a group, as we learn it in our undergraduate, is a very abstract way of defining a set with a binary operation. So a group is just something that has an identity, so something that it has an E that if we multiply any element on any side, then we get the same element back. Every element also has an inverse. So if we multiply an element by its inverse, we get the identity. And then associativity condition also holds. So if we multiply three things together, it doesn't matter which order we multiply them together.
So do you mind if I ask you, what LaTeX package do you use to get these fonts?
Oh, I wrote it myself with my own hands. On my iPad, yeah. Okay, so some basic examples of groups. For example, you can take the integers with addition. So obviously we have the identity, which is 0. Every element has an inverse. So it's negative, because if we add something to its negative, it's 0. And then associativity also obviously holds. We can also decide to look at invertible 2x2 matrices with multiplication over any field we want. And then the identity is just the identity matrix. If we multiply any 2x2 matrix by this, we get the same thing back. We also know what the inverse of a 2x2 matrix is, and we are only looking at the invertible one, so that is given to us for free. And then we also have the associativity condition holding here. Okay, I don't think about groups in such abstract ways usually. I like to think of groups as symmetries of objects. So for example, so it's an abstract way of viewing symmetries, and then you can just think of the object that it's the symmetries of. So for example, you can take some molecule. I'm not very good at chemistry, so I just drew this. I'm not very good at how to find all the symmetries, but I know that they have some, and then it's a very important thing in chemistry to understand symmetries of molecules. And then this is one application of group theory. We can also look at the Rubik's cube, and then and then it also has symmetries. And in fact, symmetries of the Rubik's cube are just moves of the cube. And the Rubik's cube is not very big, so you would think that the group of symmetries is maybe not that large, but it's actually very, very large. So the size of the symmetry groups of the Rubik's cube is this super duper big number, which is just a product of lots of 2s, lots of 3s, some 5s, 7s, and an 11.
It looks like an account number.
Sorry?
It looks like a bank account number.
Well, you can try it. But yeah, maybe Rubik Erne's bank account is this. Then you can send some money over there. So you can look at symmetries of molecules, or you can look at symmetries of the Rubik's cube, or lots of fun things, which is surprisingly big. I'm not going to go into detail of how this is calculated, but it's a fun thing to look at in your free time if you're interested. Or we can also just take the symmetries of a regular triangle. So here's a regular triangle. Its symmetries are going to be this mirror symmetry, this reflection, where this red line is this rotational angle, and then you can just swap the two things down there. And then you can also just permute it around, so you can turn it, and then you can sometimes turn it and then take the symmetries. So in total, there are lots of rotations and reflections, and there are 6 of them in total. You can also look at a regular square. This has a bit more symmetries because it just has several rotations more than the one above, just because it's a bit of a bigger shape. So it has this reflection and then lots of other reflections as well. And then it also has the rotation. And then this has 8 symmetries in total. Okay, instead of looking at some specific objects and thinking of groups as symmetries of those, we can also think about groups as symmetries of n differently colored balls. So those will be permutations. So permutation groups are, you take n, you can't really see it, but this n is just the numbers 1 to n. And then a permutation is just a bijective map from 1 to n to 1 to n. And then the symmetric group, denoted by Sn, is the set of all permutations of 1 to n. And this is actually a group. So all of the permutations possible with functions, it's quite nice. They satisfy all of the axioms of groups quite quickly. And then because they are bijective, all the inverses are also there. And then a permutation group is a set of permutations that form a group. It can be all of them, it can be some of them. So for example, if we go back to our example of a regular square, then we can take the regular square and number the vertices from 1 to 4. And then we have this rotation, which just permutes the numbers around. So, well, it's pointing the wrong way now, but like the inverse of that is just 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. And then the inverse of that is 1 goes to 4, 4 goes to 3, 3 goes to 2, and 2 goes to 1. And then we have this mirror symmetry, which is just 1 and 2 swapped and 3 and 4 swapped. We have this mirror symmetry with 1 and 4 swapped, 2 and 3 swapped. We have this one with 1, 3, and then this one with 2, 4, and then we can put those together, and then we can also do nothing. And then this is a permutation group, and it's called D8, and it will be a subgroup of S4. Okay, and then what is very nice is that every group is isomorphic to a subgroup of the symmetric group by Cayley's theorem. So if somebody is like me and likes to think about the objects that groups act on more than just think about them in an abstract way, you can just think about groups as permutation groups.
But do you mean every finite group?
Yeah. Sorry, I'm a finite group theorist, so I think about finite groups. And but yeah, maybe infinite groups is also true. Yeah.
But then you have to have an infinite permutation.
Yeah.
Yeah.
That's my point. Yeah.
Yeah.
Because assembly.
Okay. Now graphs. I guess everybody knows what a graph is in the room, but I wanted to draw some examples because I like drawing things and thinking about things. So graphs are just some things that have vertices, which are these points, and edges, which just connect some of them. So one example would be train networks. So for example, here is Manchester, Sydney, and Newcastle. There is a Newcastle in the UK as well, but today I'm in Newcastle in Australia. So like there is a train between Newcastle and Sydney, but obviously Manchester is too far, so there is no train connecting those. My other favorite graph is the Erdős collaboration graph, which is something that can model the Erdős number as well. So all of the mathematicians and maybe other scientists as well are the vertices, and then Erdős will be adjacent to his collaborators, and then because they have published papers together, and then maybe some collaborators would be adjacent to each other because they could have published papers together as well.
Okay, so let me just emphasize that your graph is not directed. So the difference between you and us is that you don't distinguish the beginning and the end. Am I right?
For now, yes.
For now, yes. So then you'll get an orientation. So what's your Erdős number?
My Erdős number is 2.
Wow, excellent.
Yeah. Okay, so these are graphs. These are not directed, but they could be directed, and later on in this talk, some directed graphs will also appear. Okay, so how can we associate a group to a graph? So this is probably not very shocking, but graphs themselves also have symmetries. These are also called automorphisms sometimes, and the automorphisms or symmetries of the graphs are just some symmetries which preserve the vertices and the edges between them. And then, so we can basically just take our graph and then associate all of the automorphisms to it. And because these are symmetries, they will form a group. So some examples, if we take gamma to be the empty graph on 5 vertices, then whatever we do to the vertices, however we swap them around, they will all preserve the same graph. So then the automorphism group of gamma is?
That's fine.
Yeah, so all of the permutations are fine. And in fact, this is not the only graph for which S5 is the automorphism group, because if we take all of the edges, then we can still do all of the permutations and preserve the graph. So the automorphism group is going to be S5. How about this graph? So this graph, we can't do every single permutation because we can only send 1 to 3. We can't send 1 to 4 because the number of edges sticking out is different. So then the only permutations we can do are 1 sent to 3 and 3 sent to 1 and 2 sent to 4 and 4 sent to 2, and they're combinations in every way. So the automorphism group will be the one generated by 1, 3 and 2, 4, which is just K for the Klein 4 group. Okay, so it's quite easy to associate a group to a graph, but is it easy to associate a graph to a group? So if you are given any finite group you want, can you find the graph gamma such that the automorphism group of gamma is exactly the group that you start with? What do you think? Maybe. The answer is actually yes. So for every finite group, you can find the finite undirected graph so that your group is the automorphism of that graph, which is quite nice. And it was proved quite a while ago. And you might ask, okay, so there is one, but what is it? Can we describe it so easily? Because with the graph, we have the graph and then we immediately know what the automorphism group is, and that is specifically given to us. How about the other way around?
So you probably use that your finite group is inside some permutation.
Yeah, kind of. So turns out that in most cases, there is actually several graphs that you can find. And something that people might think when they think about groups and graphs will be Cayley graphs. So if you have your group G, then you also have a subset of your group S, which S doesn't need to be a subgroup. In fact, it cannot be because it will not contain the identity, but it will contain inverses. Then you can define the Cayley graph, KGS, to be the graph with vertices that are the elements of G. And there'll be an edge between G and SG for every G in the group and every S in the set. So your S will just be the connection set. So all the neighbors of the identity will be the things in S. And if you multiply every vertex on the right by an element of your group, then all of these connection sets will be preserved, because then you'll have G times something is adjacent to SG times something. So then right multiplication by your group preserves this. So that is an automorphism. So it's clear that your group lies inside the automorphism of the Cayley graph. So now the question is it the same? Now you can also define the Cayley digraph as well, which will be now a directed graph that we saw a lot in the previous talk. And here you don't need inverses anymore, because if you had all the inverses, then it would be undirected again. And then the G will be pointed to SG here. Okay, so in this case, also G will lie inside the automorphism group of this digraph. And then the question still remains, okay, it's inside, but is it the same? Can it be the same? Can we just say, oh, you just take a Cayley graph and then that's the graph that your group is the automorphism group of? Okay, so let's look at the group C7, which is just the group generated by an element of order 7. So you can think about it as Z7, so with addition, and then everything is by mod 7. And then we can choose S to be our generator and the inverse of the generator to make sure that it's going to be a symmetric set. So here are all the elements of the group, and then we need to put in the edges. So 1 will be adjacent to things in S, and then every element will be adjacent to the power before it and the power after it. So this is just going to be a cycle. Okay, so what is the automorphism group of this graph? Well, we're happy because we have C7, which is just permuting all elements in a circle. But we also have another one, which is the symmetry, like the mirror symmetry, which I just will call iota. So then, and then we can put these reflections and rotations together however we want. So then the automorphism group of this Cayley graph will just be our group G, semi-direct product with this iota. So then this Cayley graph is not going to work for us because G is not the automorphism group here. It's just a subgroup of the automorphism group. However, if we take the directed Cayley graph and then we have S is only X and not its inverse, then we'll have that 1 points to X, and then we can just fill out the rest of the Cayley graph. And in this case, we still have this rotation, but the reflection is gone because of the directions here. So we're quite happy because the automorphism group is now G. So we have found a directed graph that the automorphism group is G, but the undirected graph doesn't seem to be the Cayley graph. So here's the definition, which says that a Cayley graph, gamma, of G is a graphical regular representation, or GRR, of G if the automorphism group of that is isomorphic to G. And then we can create the equivalent definition for Cayley digraphs, but in this case, we'll call it a digraphical regular representation, or DRR, if the automorphism group of the graph is isomorphic to G. It turns out that, okay, for C7, we couldn't find the GRR, but in general, we usually can. So Godzil proved in 1978 that all finite groups admit GRRs, except this list of exceptions, but everything else actually does. And then some things in the 13 groups of order 32 are, for example, some dihedral groups and A4. But it's quite, so like, if you think back to the C7 example, then the next result might make sense, because Babai proved in 1980 that all finite groups admit DRRs, except 5 groups of order at most 16. So like these abelian groups and generalized dicyclic groups here will disappear. and the 5 groups of order at most 16 will be these. So usually...
Sorry, can you remind me what it means to have an exponent of an invariant group? What is it?
So if you take any element of the group and take it to... So if your exponent is n, for example, then if you take any element of the group and take it to the power n, then you get the identity.
Oh.
And then the generalized dicyclic is kind of a similar vibe to the dihedral groups, just a bit more sophisticated. Yeah, so it turns out that Cayley graphs are usually good for us. And then if Cayley graphs are not the answer, then lots of information is still known. Okay, so we have now seen that groups and graphs go hand in hand, because it's very easy to go from a graph to a group, and it's very easy to go from a group to a graph. So in some ways, groups and graphs are maybe kind of the same. So can we study some graph-theoretic problems through a group theory lens? So you have a graph theory problem, it's very fun, but maybe you like groups more, and then can you just study it like that? So I'll show you an example where you can. So here is the graph theory problem that I want to study through a group theory lens. So we'll have gamma to be a simple graph on n vertices. It's going to be undirected and no multiple edges or no loops. So here's the question. Does the complement of gamma, which is just all the edges that are not in our graph gamma, contain an isomorphic copy of gamma? So you can think about it as, can I take a complete graph and color some edges pink and some edges blue so that they look the same inside and they are disjoint? Okay, so some examples. Let's look at this example, and then our gamma is the pink edge. Can we find an isomorphic copy in the complement? Yeah, lots of them. For example, this one. So that's very good. So in this case, the answer to the question is yes. Okay, next example. You take this graph, which is the 2 pink edges. Can we find an isomorphic copy in the complement? Yes. For example, this one, very good. How about this? 2 edges far from each other. Yes. For example, this one, very good, very happy. How about this triangle? Yes. So here we go. We found it. Very good. Maybe the answer is always yes. How about this one?
No.
No. We can't, because here we have one vertex that is adjacent to 4 things, but in the complement, every vertex is adjacent to only 3 things. So of course we cannot find something like this. So here's the next question, which is, what is the largest integer m such that every graph gamma, which has m vertices or less, can be packed twice into Kn? So we have an upper bound here, which is
packed twice, you mean done in 2 different ways, simply.
Yeah, so that they are next to each other and the edges are distinct, so they don't have an intersection. Okay, so there is an upper bound, which is n minus 1. And this one, we can just see from the example from the previous page. So you take your gamma to be the graph which has 1 vertex adjacent to everything else. So it's the complete bipartite graph k1 and n minus 1 as well. And then we cannot pack it twice into Kn, because in the complement, every single vertex will have n minus 2 edges coming out of it, and we need n minus 1. So we clearly see that for that, we cannot pack it twice, but maybe everything that has less edges than this one can be packed, and that's actually the answer. And it was proved by Burns and Schuster in 1977 that any graph of your choice, which has less edges than this star of the counterexample, can be packed into Kn twice, which is quite cool. And this was proved using just graph-theoretic methods, and it's a very nice result. Okay, now on to some algebra and group theory questions. So take the symmetric group on n points, and I will be just the numbers 1 to n, and consider x, which is size 2 subsets of I. And here's the question. What is the largest integer k such that for any subset of these pairs of size k, there exists some element of our group, so that if you take all of these pairs and look at their images under this permutation group, then the intersection will be trivial. So this sounds a bit familiar, right? Because what are edges in a graph? Size 2 subsets of the vertices. So if we think of 1 to n as the vertices, and then the size 2 subsets are the edges, then if we take a set of these edges, it's a graph. And then since the symmetric group can send everything to everything, then A and A to the G, if their intersection is trivial, are just two graphs that can be packed into Kn. So it turns out that question 2 and question 3 are the same. And so their answer is also the same. So we had a graph theory problem, and now we have a group theory problem. Doesn't mention graphs at all. So that's quite nice. So we can also think about generalizing this problem to any permutation group. So in fact, I would like to generalize it to transitive permutation groups, where transitive means that for any 2 points in omega, that's where, so omega is the set that we're permuting. You can think of it as 1 to n, or you can think of it in a more abstract way. And then transitivity means that for any 2 points, you can find an element that sends one of them to the other. And then that is something that, for example, the symmetric group will do.
G acts on gamma.
Yeah.
Is it G acts on that set? That's what it means.
Yeah, so G acts on that set transitively.
Oh.
But yes. And it could act it could act just not transitively if we didn't have this condition that you can send any point to any other. But if it's transitive, we need that condition. Okay. So we also want our omega to be finite, and we want it to have size at least 2. And we say that a subset of omega is self-separable for G if there exists an element of G such that this set A and its image G sends this image where G sends it is disjoint. So it's the same idea as before. It's just we don't have necessarily all of the permutations, we just have some of them. And then we say that it's not self-separable otherwise. We can then define this sep G omega, which is the separability number of a permutation group, which I will sometimes say that it is sep G if the action on omega is obvious, to be the smallest number such that there is a subset of omega of that size, which is not self-separable. And that is the same as saying that it's the maximum number T, such that for any set whose size is strictly less than T, A is self-separable. So this is actually one more than the answer to our previous questions, because this is the one where we can't achieve this anymore. So if we take Sn acting on X, or our graph theory problem, then the separability number is going to be n minus 1.
Sorry, let me ask you a very silly question. How important is that you have a group instead of a semi-group in this discussion of separability?
So far, not important. Later on, transitivity will also be quite important. So I don't know if you can have a transitive semigroup. I don't know much about semigroups.
Well, I mean, the definition of transitivity is just the same, but
yeah, but I don't know, because in some of our results we use some theorems of Neumann on groups. So I think some of those might not hold for semigroups, but I never thought about it. They might hold for semigroups. It's an interesting thing to consider, but I never thought about it before. But yeah, maybe you should think about it.
No, I have so many things to think about.
Yeah, okay. So we can come up with an upper bound quite quickly, but our upper bound is not that exciting. So the upper bound will just be the size of omega plus 1 divided by 2. So this upper bound is quite obvious, because if I take a set that is larger than half of my big set, then obviously wherever I take it, there's not enough space, so I will need to have an intersection. So this bound doesn't seem so exciting here, but turns out that this is the best we can do in the realm of transitive permutation groups, because if we take Sn acting on just the points 1 to n, so instead of on pairs, it's just acting in its natural action of permuting the numbers 1 to n, then if we take any set of size less than this upper bound, so n plus 1 over 2, then the complement of that set we will just denote by ak plus 1 to an. And then we need to find a group element such that a to the g will lie inside this complement of a, and then we'll show that it's self-separable. So we can always do this, because we can just take our element that sends ai to a k plus I. So it's like swaps these out, and then the a to the g that we get will lie inside this omega without a. So then that gives us that the separability number will be at least n plus 1 over 2, and that was our upper bound. So the separability number will be n plus 1 over 2. So this bound, however unsatisfying, it's sharp. Now, we can also think about a lower bound, and the lower bound is a bit more satisfying here, because with my collaborators Marco Barbieri, Marusha Lekshe, and Primoz Potočnik, we showed that if G is a group acting transitively on omega, where the size of omega is n, then the separability number is at least the square root of n. And then sometimes I will just refer to this 4 of us as BLPR, so then I don't need to write down everything, so you'll know later if that appears, that is just us. So we know that the previous bound was sharp, so you might ask if this bound is sharp. What do we think? No, but almost. Because if we think back to our first example, it was Sn acting on pairs, and then the separability number was n minus 1, and then the size of the set that we're acting on is just n choose 2, because that's the number of pairs, and that's just n times n minus 1 over 2, and the square root of that is, for a very large n, is basically n minus 1. So this bound, pretty good. Thankfully, we also have a sharp bound, which is just 1 over 2 times the size of a point stabilizer, where the point stabilizer is just the elements of the group that send alpha to alpha. So it's 1 over 2 times the point stabilizer plus the square root n minus 1 over the point stabilizer plus 1 over 4 point stabilizer squared. And this one is sharp. So I'm going to show you an example of this now. I quite like C7, as you can see. So I'm going to show you an example of C7, which will be generated by beta, and then it's going to be acting on itself by right multiplication. So just multiply itself. So sets of size 1 are just going to be powers of beta. And then obviously, if you take any power of beta and then you multiply it by beta, you'll get something different. So all of these sets of size 1 are going to be self-separable. This also just follows by transitivity as well. If you take sets of size 2, for example, you can take this set beta and beta to the 5. If you multiply this by beta, then that sends it away to something that is completely disjoint from it, beta squared and beta to the 6. And then that means that this set is also self-separable. And then we can check for any sets that they are self-separable of size 2 as well. Sets of size 3 is not necessarily self-separable. So let's take this set A, which is beta, beta to the 5, and the identity. So to check if this is self-separable, we need to see all of the possible places that it's sent to by the action of the group, and then compare whether there is an intersection or not. So here is the orbit. So here are all of the sets that we can get to by acting on this set. There is not so many of them, so we could just compare all of them and then see if there is an intersection, or we can do something more fun and draw this graph. And this graph is, maybe some people recognize it. No, it's called the Fano plane, and it's something that algebraic combinatorists quite like usually. So this is something where all the lines are these sets in the orbit of A, and it's the Fano plane, and the Fano plane is a projective plane. And what we know about a projective plane is that all lines intersect in a point. So instead of looking at this orbit and checking for things, we'll just use this knowledge. And then that tells us that A is not self-separable. But we showed that for any set of size less than 3, we will always be self-separable. So then the separability number will be 3 in this case. So let's plug this into our bound from previous. We can also see that this is a regular action, and the regular action is just defined by having the point stabilizers equal to 1. So if we plug this into the bound that I said was sharp, then we'll get that this bound actually gives us a 3. And then that's our answer. So we attained that bound.
So how did you define G alpha?
G alpha is the point stabilizer. So it's all the elements in the group that send alpha to alpha. And then the definition of regular action is that alpha is only sent to alpha by the identity. Okay? And then we actually classified all of the groups, all of the transitive groups which attain this bound. So this bound is a lower bound for everything. And then there is equality if and only if G is a regular group of collineations of a projective plane, which, for example, will be some of these cyclic groups. Okay, I don't know how much time I have now because I don't know when I started.
Oh, yeah, you started about 1:15, so
You started.
about 20 minutes.
Oh, I still have 20 minutes. Okay, perfect.
But we probably want to finish a bit early, so.
Yeah, I think I will probably finish earlier. Okay, so we can find more results for regular groups in general. So regular groups are just going to be these groups that act on themselves by right multiplication. And then the point stabilizer is just going to be the identity for all of them. And then in this case, A to the G will just be A multiplied on the right by G, because the action of G will just be on the right. So in this case, if A and AG intersect, then the element G will lie inside A inverse times A, because that means that there is an element A1 and A2 in A such that A1 is equal to A2G. And if A is not self-separable, then this holds for every G. So in that case, we can see that A inverse A is equal to the whole group. And this is something that is a well-known thing in abstract algebra, and it's called a difference basis. So a difference basis is a subset of G such that A times A inverse is the whole group. And so we can see that the separability number of G in this case will be the smallest size of a difference basis. Lucky for us, the difference basis has been studied, and Lev and Cosma have this result that every abstract group of order n admits a difference basis with the size of the difference basis at most 4 over square root of 3 times square root of n. And this means that if G acts on itself regularly, then sep G will be between square root of n and 4 over square root 3 times square root of n. And you can see that these bounds are actually very close. So in this case, we have that this separability number is sandwiched between these linear multiples of square root of n. So this is basically square root of n. And this makes us think maybe this is true in general. It's not necessarily so pretty in the general case, but I'll show you some results here. So a transitive group can be either imprimitive or primitive. It is imprimitive if it preserves a non-trivial partition, and it's primitive if it doesn't. And then our result for imprimitive groups is if G is imprimitive with a block system of cardinality B, whose blocks contain A points, then the separability number is at most A plus B minus 1. And if G embeds into this imprimitive wreath product, then we can see that the separability number is between the separability numbers, the product of the separability numbers of K and H, and the sum of the separability numbers of K and H minus 1. And I will show you the proof of this star in the next slide. So you can also see this partition, but because it's also very nice. So if we have an imprimitive action and then it preserves a partition of, this is the partition we're preserving, the block system, we have B blocks and they all have size A. We need to find a set of size A plus B minus 1 that is not self-separable. So wherever we send it to, it will always intersect with itself. I don't know if anybody wants to guess it.
Is it going to be sort of one block and then
Yeah.
across the block?
So if we take a full block and then we take 1 point in all of the blocks, then every permutation that preserves this block system, wherever it takes A, we're going to have a full block, and then we're going to intersect every other block in 1 point. So then A will intersect all blocks, and then A intersects A to the G is going to be not empty. So A is not self-separable and A has size A plus B minus 1, and then the result follows. So we have seen that for the imprimitive groups, the separability number is driven by the separability number of this K wreath H. So that is kind of a reason for us to focus on primitive groups, because in primitive groups you can think of as putting some primitive groups together. And then the primitive groups are transitive and do not preserve a non-trivial partition of omega. And then in this case, we have this question that if G is primitive and the so-called is not the alternating group, that is just there because of Sn has this weird natural action where the separability number is very large, so we have to rule that out. But in general, if G is primitive, can we find some constant C for every epsilon greater than 0, such that the separability number is bounded above by some C times n to the 1/2 plus epsilon? So can we have the separability numbers sandwiched between square root of n and something that is close to square root of n in some sense? And then to this question, we have a partial answer from our result. And our partial answer says that it is a yes for some of them. And these some of them are almost simple groups in standard action. So you can think of that as an or Sn acting on subsets of the numbers 1 to n, or you can think of them as classical groups acting on subspaces of degree k. So for example, PSL and Q, which is kind of PSL and Q is basically just all of the invertible matrices over a finite field. And I can show you a proof idea for this standard action. So if we take PSL-DQ acting on K subspaces, which I will just denote VK, and then we will have K even. Then if we take this U, which is the subspace of dimension K-half, that has basis, the standard basis E1 up to EK-half, then we can define this set A, which is all the subspaces of dimension K, which contain this subspace of dimension K-half U. Then, for every element of the group, there exists some XG, which is something that contains this U and its image under the action of G inverse. So because these two things are K-half dimensional subspaces, of course there will be a K-dimensional subspace that contains both of them. And then U to the G plus U will be contained in XG's image under G. And then this will be contained in A and A's image under G, because it contains U to the G and U as well.
I'm wondering what you mean by a natural module.
So the natural module is just no. So if you have there is markers. So you can think of PSL-DQ as D by D matrices over FQ, and then the natural module is just FQ to the D.
So it's a free module.
Oh.
Actually, FQ is a field, right?
Yeah.
So it's a vector space.
Yeah, it's a vector space.
D-dimensional vector space. Why call it natural module?
Because of representation theory. Sorry. It's when we work with almost simple groups in primitive actions, we just call it the natural module, because there's lots of modular representations there, and then this is just the natural.
Also, I believe that what you call the regular action is simply free action, because it all stabilizes at trivial for every point. This is simply.
In permutation group theory, we call it regular action, but maybe.
For any group acting on any space, you know what it means, free action. It means all stabilized groups, subgroups are trivial.
Regular is free and transitive. Regular is free and transitive.
Oh, free and transitive. Okay, then I'm yes. Okay, this is good. This is what I wanted to hear.
Okay, good. Thanks. Right. So then A is not self-separable, and A has size n to the 1 over k. K over 2. So as n gets really large, this is basically the square root of n. And this gives us the result. And then just to finish, I have given you the classification of groups which attain the sharp lower bound. So now I'm going to give you the classification of groups which attain the sharp upper bound. So which groups can attain this? So for imprimitive, we know from our result that the separability is bounded above by a plus b minus 1. and then A times B is n. So the only time that we can attain this bound is when A is 2 or B is 2, because if one of them is larger than 2, then the upper bound will be smaller than this sharp bound. And then for primitive groups, we know that Sn and An in their natural actions attain this bound. And with my collaborators, we have classified all of the possibilities. So if G is transitive on omega, where omega has size n, then the upper bound is sharp if and only if G is primitive and is An, Sn, or 29 small groups, for example, M24 in degree 24 or PSL27 in degree 8, or G is imprimitive and is a subgroup of C2 wreath sim and half, or sim and half wreath C2, or 60 small groups, for example, this C2 wreath M12 in 24 points. And this is all I wanted to say. Thank you.
Thanks, Kamilla. Any questions?
May I ask you a very difficult and tricky question?
Let's try.
Okay. Which team do you support, Manchester City or Manchester United?
Oh, I really couldn't care less.
Good answer.
Sorry. I wish them the best, both of them.
Okay, but now more seriously, could you go back to the slide defining the self-separability? I'm just trying to wrap
It might
my
take
head
a while.
around it. Yeah, no. So the condition is that A and AG must be disjoint for some element G in your group. But I'm trying to somehow understand this.
Yeah, it's a bit of a convoluted definition, because it's there exists for all disjoint so many
but
things.
It's a concept that depends on your choice of transitive
action. Yes.
So it might differ if you choose a different action.
Yes, exactly.
Okay.
So that's why we have, well, I call this sep G because I always told you what action we're considering. But in general, you need to have it as G omega, because it really depends on the action that you choose. Because also A is going to be a subset of your omega. So you can't even answer it without specifying the action.
Because I think this question makes perfect sense if you go to topology, they ask you to acting on a two-sphere. And you can ask yourself, what is a nice, I don't know, closed subset on the two-sphere, which is self-separable?
I think this is a very exciting parameter, and I think it could be used in lots of places.
Yeah.
So
it's not bound to discrete.
No. So I think if you take anything acting on anything, you could define it. Just might be not so easy to solve.
Yeah, it's interesting. And another thing which comes to my mind, you see, the theory of quantum permutations is very well developed. And it actually has to do with graph theory, because there are some very difficult problems in graph theory, like you have two directed graphs and you want to know whether they are possibly isomorphic, and you cannot prove it.
Yeah.
And then what you do, you study quantum symmetries, quantum automorphism of a graph, these are quantum books, and then you see they're an isomorphic bang, so graphs must be non-isomorphic. But you cannot detect it with classical symmetries.
Wow. Yeah, I never heard much about these quantum permutation groups, but it's interesting.
I can tell you at lunch.
Yeah.
Sorry, we've got a question online.
No, it's just.
Okay. Anyone else? Well, as we've run over time, then we should probably stop there. So thanks, Kamilla.